This is intended to be a bare bones basic recovery of infrared and UV spectroscopies, so we aren't going into a lot of details. If you need more detail, which you probably will, you need to reference your textbook or supplemental information provided by your instructor. If you're at Chandler Gilbert, Mike McFablin has a bunch of supplemental materials for you. What we're looking at with almost all forms of spectroscopy is the electromagnetic spectrum. And the different ranges of energies within the spectrum cause certain molecular effects. So we could then go through and reference those effects based off of them. Okay? And we've seen some of these likely before. The focus of this video is looking primarily centered around the visible spectrum. So if we go higher in energy than visible, we get the ultraviolet energy spectrum. If we go lower, we get infrared energy. Those two energies do different things to our molecules. It turns out that when we're looking at ultraviolet energy, it is enough energy to cause an electron to jump orbitals. This is the explanation for why we see fluorescence. It's also the explanation for why we can use absorption spectroscopy. It's ultimately ultraviolet light that is being absorbed. Infrared energy is lower in energy than ultraviolet. Well, ultraviolet is causing an electron, an insanely tiny particle, to jump orbitals. Well, if we move to an even lower energy, we're going to get less things happening. Electrons are so tiny, we're not even moving the electron. Really all that's happening is we're causing the electrons to just kind of wiggle a little bit. Because the electrons are found in bonds, we now see the bonds wiggle. Okay? That wiggle is a vibration that we can detect using effectively the same technique in both forms of spectroscopy. So let's start with our higher energy one. If we looked at kind of a basic picture of atomic orbitals, we've got our nucleus at the bottom, followed by our 1s orbital, our 2s, our 2p, 3s, 3p, 3d, etc. Okay? And yes, we get multiple of each of those. If we went through to look at, say, your, I'm going to reference them incorrectly, but your Balmer series or Rutherford's model, what we were talking about is placing our electrons in there, and the atomic line spectrum that we were seeing is that if we took that electron and excited it up to a higher energy, when it comes back down, it has to emit some energy. If that energy falls in the visible light spectrum, we get an atomic line spectrum. Okay? So it's literally just the electrons jumping between these orbitals. The gap between those orbitals corresponds to the energy. That's the color of light we see. Okay? When we do UV spectroscopy, really what we're concerned about then is not so much at the emission, we're concerned about that absorption. How much energy does it take for it to go up? We would see this because we fire light at our sample and we've got a detector on the other side of it. If the detector sees the light, well, the sample didn't absorb. If the detector doesn't see the light, then the sample absorbed the light. And we now have an absorption spectrum. Okay? So that's its basic level with stuff you guys have probably already seen. It very quickly scaffolds up because we now shift to organic molecules, and organic molecules are vastly more complex. Okay? In that complexity, what we now have to move to is, instead of atomic orbitals, molecular orbitals. And I know these pictures look nuts, but really what you're focusing on is pretty much the same thing we saw in the other system. We have some molecular orbitals, and what's happening is we start in our ground state, we hit our particle with ultraviolet light, the electron then jumps to a higher energy orbital. The most likely transition is going to be the closest orbital. Okay? And that's it. That's UV spectroscopy. Okay? So we're just talking about how we jump between those orbitals. The pictures that we're seeing here are associated with how those orbitals or those molecular orbitals are formed. Okay? That's a little bit more challenging of a concept that we will see in the first couple chapters and will continue to potentially use. At this stage, keep it kind of simple. They're just orbitals that are jumping around. Okay? In this case, what we are referencing or the most likely transitions are your pi systems, and that is because the pi systems have the closest gap in energy. Okay, and actually I'll step back a little bit. If you vaguely remember your molecular orbital theory, maybe from 151, you might have seen something like this, where you had pictures along these lines, and you called these sigma and sigma star, all that fun stuff. And if you vaguely remember that, you might also vaguely remember, whoops, that your pi star and pi are usually in between. Okay, which means the gap between your pi and your pi star is smaller. That's the more likely transition. Could we also see a transition from the sigma to sigma star? Yes. That transition requires more energy. It's a larger jump. That more energy now starts to push into the limits of UV spectroscopy, and we can't really detect it as cleanly. Okay? So what we're largely looking at is our pi system. Well, pi begins with p. What orbital begins with p? P orbitals. So what we're looking at is p orbitals and how they align. When we bring together p orbitals to generate the molecular orbitals, the more p orbitals that align, the closer in energy the orbitals become. Okay? So if I'm going to look at the energy required to eject an electron in this first system, I've got an energy gap that's roughly that much. If I move to the next one where I have more p orbitals there, notice that the energy level has slightly increased for that highest energy electron. You'll also notice that the energy level for the lowest unoccupied orbital is a little bit lower, which means when I look at the energy difference between those two orbitals, that energy gap is a little bit smaller than that for the first one. Okay? That comes in handy because that's what allows us to use UV spectroscopy. Because the orbital overlaps are slightly different, the energy for the most common orbitals, the highest energy or the highest occupied molecular orbital, HOMO, will be in a different comparative state to the ground state of a different molecule, and the LUMO, or the lowest unoccupied molecular orbital, LUMO, those gaps are now different. Because the gaps are different, the amount of energy used to transition between them are different. We can see that in our detector. Okay? That's ultimately what UV does, is it's just saying, well, they're different. Because they're different, we can sort of identify the molecule. Okay? That's all you really need out of UV spectroscopy, okay, at this stage. We'll talk a little bit more when we get further along in the lecture. Okay, so the next part is infrared spectroscopy, which is the primary reason for this video. Okay, infrared energy is lower in energy, and so it can't cause the electrons to jump around. Instead, it just causes the molecule to move or vibrate. Okay, well, it's still causing the electrons to kind of change. Well, now the question is, well, where are electrons located in a molecule? Okay, well, the highest energy electrons in any given molecule is going to be located in the bond. Okay, so when we draw out Lewis structures, that line is drawn because there's a pair of electrons there. That's what it means. Okay, so when we're talking about IR spectroscopy, we're talking about the energy that causes that bond to move a little bit. Okay? How it moves changes the energy that's going to cause it to move. Okay? That's that blue light that's coming in, or that blue arrow. So what we end up having to do is make some approximations on what we see and understand about bond vibrations. So really all IR is doing is causing a single bond to vibrate. Okay, the easiest example is shown right up on top. What we're doing is effectively saying that a bond is a spring that connects those two atoms, that keeps them together. Okay? If the spring breaks, we don't have a bond. Okay? That's it. That spring can cause those atoms to oscillate back and forth on each other. And what we're looking at is a stretch of the bond. Okay, and this is at its most basic, simple level. That stretching force gets tied to the spring constant if you really wanted to deal with physics. Okay, I don't really want to, but that's what's being compared. So what's happening is we have our molecule in its equilibrium bond length, so it's just steady state. We fire IR light at it. Okay, if that IR light happens to match the spring constant for that spring, it's going to cause those atoms to kind of bounce back and forth. It's going to cause either a compression or a stretching. And we're going to oscillate back and forth between those. They're actually inverses of each other. Just like with UV, we can now see that the light hasn't made it through the sample. Okay, we have a detector at the other end that says, hey, the light didn't make it through. The molecule's absorbing it. Okay? Remember, that was the simplest way to look at it. There are lots of bonds in molecules. And molecules are a lot more complex than just two atoms, which means you can get different types of vibrations. Okay? And that's what's being shown on the bottom. You can get something known as symmetric stretching. And let's hold a second here. You can get something known as symmetric stretching. Both of those hydrogen atoms are pulling away from the oxygen at the exact same instant, and then of course coming back at the exact same instant. Okay? Or you could think about it as someone just punching their arms out at the same time, in sync with each other. If we look at antisymmetric stretching, we punch the right arm, and as we pull the right arm back in, we punch out the left arm. Okay, so it's kind of an, I would call it an oscillation, but really what we're looking at is an antisymmetric stretch. What's really exciting about this is your instructor is literally doing these hand motions while recording this video alone in his office. It's a bit silly. The last one is a bending one, or a scissoring action, or one of the last ones is a bending action. Each of these generates a slightly, or requires a slightly different amount of energy, which means we would see a different absorption of energy in our spectrum. Okay? With UV spectroscopy, you didn't see me show anything kind of beyond this. We just said this is what it does, and we left it alone. We will come back and look at UV spectra, but for the most part, we don't have to stress about their spectra. IR, on the other hand, we do. So now we have to shift to looking at an IR spectrum. Where do these things show up? So what we've got here is a nice kind of general form here. If you take a look at the, I believe that is your x-axis along the bottom, it's referencing in wave numbers, or inverse centimeters. So centimeters is in the denominator. Okay. What things, according to light, are measured in centimeters? Well, wavelength is in centimeters. Okay. And if I do h nu, I've got energy. So inverse wave numbers is effectively energy. Okay. It's directly tied to it. Okay, to that concept. Why don't we represent it as wavelength? I honestly don't know. It might be to avoid confusion with ultraviolet spectroscopy, which is reported in wavelength. Okay, so when we're looking at our x-axis, we're really talking about the energy, okay, of the light that's being used to excite the bond. Okay? On the y-axis, we see our percent transmittance. Okay, which is related to absorbance. Depending on the form of IR spectroscopy you're looking at, you might see percent transmittance or absorbance. It is typically presented as percent transmittance. This means a signal running close to 100% up here at the top means the light didn't interact with the molecule. It went straight through onto the detector. Okay? When we see a peak, you might say, well, that looks like a very weird peak because it's going down. We're inverting it because of the transmittance here. That bottom part is what we would reference as a peak. Okay? That's saying that we did get an interaction between the sample and the light. Okay? So now we've got our spectrum. you'll notice that we see a variety of different ways that we could see a peak. We could see peaks that show up with relatively low intensity. We look at this one, we're saying this is ballpark 70% transmittance, so a relatively minimal absorption of light or interaction with the light. We have other signals, like way down here, that 0% of the light passed through the sample. Okay? So there's a very strong interaction between the frequency of the light, or the energy of the light, and the bond vibration, which means no light passes through. Okay? So when we talk about IR signals, we can reference the intensity of the transmittance, okay, or that peak. And it's usually strong, medium, or weak. So S, M, or W. Okay? This example here isn't the greatest, and unfortunately I don't have any in this video to represent this, but we also have another thing that we can compare. Not so much the intensity of the signal, but how broad the signal is. So if we take a look at this green peak, that's pretty intense, and so is this one here. Okay? They're both pretty intense signals, but they do have a different structure or appearance about them. If we take a look at the green one, highlighted in red, of course I did that, let's go through and make it Christmassy. If we look at that base, this is kind of a broad peak. Okay? It's intense, but it spans kind of a large range. Admittedly, this is not a broad peak, but it's broader than, say, the red one. Because when we look at the red one, I can barely even draw arrows in there because the width of that peak is so tiny. So when we talk about IR, we get the intensity, strong, medium, and weak, and we also reference something about the breadth of the signal, which is usually broad or sharp. And that's it. Okay? So when we talk about IR spectroscopy, it's really just a game of matching. Is it strong, medium, or weak? Is it broad or sharp? And that's it. Okay? There are other things that we can factor in. The last big one, which is probably going to be really important for you, is, as a general rule, about 1500. You will see when you look 1500 and lower that you get a crap ton of peaks. You get so many peaks and so many different things happening in there that it usually takes an expert to actually interpret that. Ask yourself, are you an expert? No, you can ask. Oh, you're not? Okay, ignore it. Don't even worry about it. Okay? With a little bit of a caveat. There is useful information in there, and if you get nothing from out here, then you should look into that range. Okay? So you can't always just ignore it. That range is known as your fingerprint range. So like in class, when you identified me as your teacher, nobody came up and fingerprinted me, even though that's an accurate way to represent who I am. Why'd you not do it? It's a lot of work. Okay? So most of the time, we'll spend our analysis in the range greater than 1500. I personally like to say 1600 and above is where I interpret, because there's still a lot of things that show up in that 1600 range. Okay? So now, how do we use this? Okay, well, remember I said strong. What did I say? Strong, medium, weak, and broad or sharp. Okay, so now what we would do is tie this back to all the possible structures or bonds, because that's ultimately what we're looking at in IR, is bonds that could possibly exist. So you might see a table like this. Okay, for those of you panicking and not being able to breathe, take a second. It isn't as bad as it looks, primarily because this is as bad as it looks, but we're not going to use it. If we go ahead and take a look at this form of table, on the left-hand side they're identifying the different functional groups, and if we look at an alkane functional group, okay, that's what we would expect to see. So they're referencing where the signal shows up, and if you look really carefully, that says S and S. Okay? So what they're referencing there is the strength of the signal. So they're saying we would expect for an alkane functional group 2 strong peaks in that range. Okay? That's ballpark what this is saying. Okay? It is very difficult to interpret this, So instead what I would do is practice. Look at a bunch of different spectra and start to get a feel for what things show up where. Okay? Practice is a bit tedious, but it's really your best bet when it comes to dealing with IR. Okay? The interpretation, which is the next fun part, when you do an analysis on an IR, less than 30 seconds. So within 30 seconds, you should know roughly what bonds are present in that compound. That's kind of the speed that you want out of it. Okay? So, the last part that we'll go through here is look at some kind of summary things. This slide right here, IR reveals information about bonds and bonds alone. Okay? We've got a bunch of different signals. What do I have? 6 different bond types with some descriptions of where they show up and then the intensity or breadth of the signal. Okay? Those 6 should absolutely be memorized. All right? There isn't a question there. You need to nail those ones down because you will see those frequently. Okay? I have a secondary list of another 6 that adds a little bit more information and it gets some nuances behind it. I would highly recommend you also memorize these because this is what's going to really allow you to differentiate on multiple choice exams. Okay? This is where your big differences show up and they can throw all sorts of kind of nuanced questions at you. Okay? To end with, we've got 4 spectra and we'll go through these really fast. So take a minute, pause, do as much analysis as you can, and we'll go ahead and start. So analysis 3000, that's just under 3000. This is CHSP3. That's a 3 for the record. And then this one shows up, that's 15, 16, 17. This is a carbon-oxygen double bond. That's all you would be expected to draw. Okay? You will notice that there is a sequence of peaks out here. You might say, well, why don't we analyze those? Because those are a tricky sequence of peaks, and we can talk about that if you would like. This is where the practice of looking at spectra comes into play. Okay? So, spectra 2. Take a second to pause and do the analysis as best you can. And here we go. We have OH. We're at that 3000 line again. CHSP3. And done. Okay? Well within 30 seconds. Problem number 4. Take a minute to pause and do it. Whoops. Now I'll go ahead and show it. 3000. This signal just greater than 3000, so this is again a CH, but this is from an sp2 hybridized carbon. Over here, because it's under, is CHSP3. Hybridization is going to become important. You got to watch out for it. This is a dangerous peak for me to analyze because I know a little bit more about the spectra and I have evidence to suggest it. I'll identify it. That's a carbon-carbon double bond. Okay? Notice I'm providing all the information I can. The rest of it I'll ignore. Okay? And the 4th one. Here we go. We got another spectra. Take a minute to pause. Do what you can. And here we go again. Wow. Okay, so this one becomes a little bit harder. Usually I'd recommend a ruler. Oh, that's sitting right on the line. I would call this CHSP3. And then here's where some people can kind of freak out. I might write CHSP2. Notice I'm writing it in a different color because I'm going to follow this with a question mark. Okay. So if I'm going to rely on analysis, I'm not going to base my answer on that being a CHSP2. I'm going to say maybe it's a CHSP2. I don't really know. Okay. Last one. This shows up 1650, 1700. This is a carbonyl, carbon-oxygen double bond. And done. Okay. For extra references, here you go. This is the end of it, so I'll let you pause the video as you see fit to go through and read those. Most of this information, if you're in Mike's class, is found on Canvas. Feel free to ask him to post it if he hasn't posted it yet.